Support vector machines have two key hyperparameters that directly impact performance, C and gamma. Tuning them correctly can mean the difference between a model that generalizes well and one that either overfits or underperforms. Let's start with C, the regularization parameter. C controls the trade-off between a wide margin and classification accuracy. A low C means the model is more tolerant of misclassified points, leading to a wider margin, but a higher chance of errors. A high C, on the other hand, tries to classify every training point correctly, leading to a narrower margin and a model that might overfit. The challenge is finding the sweet spot, where the margin is large enough for generalization, but not so large that the model loses accuracy. Then there's gamma, which comes into play when using RBF or polynomial kernels. Gamma controls how much influence a single training example has. A low gamma means each point has a large influence, resulting in a smoother decision boundary that may underfit the data. A high gamma means points have a very local influence, leading to highly complex boundaries that might overfit. If gamma is too high, the model memorizes the training data, performing well on it but failing on unseen examples. But how do we find the best combination of C and gamma? That's where hyperparameter optimization techniques come in. Grid search. This is an exhaustive method where we test multiple values for C and gamma in a predefined range, systematically checking which combination performs best. It's thorough, but it can be computationally expensive. Random search. Instead of testing every possible combination, random search picks random values within a range. It's faster than grid search and often finds near optimal values with less computation. Bayesian optimization, a more advanced technique that intelligently selects hyperparameter values based on past performance, gradually improving efficiency and accuracy. To ensure the model is truly optimized, cross-validation is used alongside hyperparameter tuning. Instead of just testing on a single training and validation split, the dataset is divided into multiple folds, and the model is trained and evaluated on different subsets. This prevents overfitting and helps us determine the best parameters that generalize well to new data. Ultimately, tuning an SVM is a balance between flexibility and stability. Too much complexity and the model memorizes the data instead of learning patterns. Too little and it oversimplifies, missing key relationships. Once we've fine-tuned our SVM, it's time for the real test, implementing it in Python and seeing how it performs on actual data, because understanding SVMs in theory is one thing, but applying them in the real world, that's where things get really exciting. Let's bring all this theory to life. Understanding SVMs in theory is one thing, but actually implementing them, that's where the real magic happens. So let's dive into how we build an SVM model step by step using Python. It all starts with the data. Raw data is messy. It might have missing values, outliers, or features that are on completely different scales. Before training an SVM, we need to clean it up. That means handling missing values, normalizing numerical features so they're on the same scale, and encoding categorical variables into numbers that the model can understand. In Python, we use pandas for data wrangling and scikit-learn for preprocessing. This ensures that our model learns from clean, structured data instead of getting confused by inconsistencies. Next, we need to split our dataset. We can't just train on all the data and hope for the best. We need to leave out a portion of it, usually 20%, for testing. This allows us to evaluate the model on unseen data and see how well it generalizes. A model that performs well on the training data but fails on new data, that's overfitting, and we want to avoid that at all costs. Now it's time to build the actual SVM model. In Python, it takes just a few lines of code. We use scikit-learn's SVC class to create the model. This is where we decide which kernel to use, linear, polynomial, or RBF. If the data is simple and linearly separable, a linear kernel works fine. But if the patterns are more complex, RBF is usually the best choice. We also set our hyperparameters like C and gamma, which we tuned earlier to get the best performance. Then comes the training step. This is where the SVM learns from the data, figuring out the optimal hyperplane that separates the classes with the widest possible margin. Training is quick on small datasets, but can take longer on larger ones, especially with complex kernels. Once training is done, the model is ready to make predictions. Now we test it, we feed it the test data and compare its predictions to the actual labels. But raw accuracy isn't enough. We need a deeper evaluation using precision, recall, and F1 score. These metrics tell us more about how well the model is handling different types of errors. For example, if we're classifying emails as spam or not spam, we don't just want high accuracy. We want to minimize false positives, where important emails get mistakenly classified as spam. If we're dealing with two-dimensional data, we can even visualize the decision boundary. With a little bit of plotting, we can see exactly how the SVM is dividing the space between classes. It's a great way to get an intuitive sense of how the model is working. And just like that, we've built a working SVM classifier. A few lines of code, some careful tuning, and we have a powerful model ready to classify new data. But classification is only one side of the coin. What if instead of predicting categories, we need to predict continuous values, like house prices, stock trends, or temperature forecasts? That's where support vector regression, or SVR, comes in. And the way it works might just surprise you.